All right, welcome 1.3 Secondary Math 2. For 1.3 we talked about learning numbers in the real number system. There are a bunch of different kinds of numbers. Everything inside of this box is a real number. There are real numbers. There are imaginary numbers. Imaginary numbers aren't like make-believe numbers. That's different. A lot of electrical engineers use imaginary numbers, so they are used in real life. We will talk about imaginary numbers in a future lesson. Today we're just talking about the real number system. Now inside the real number system, it's broken up into two categories. The first are the rational numbers, and the next are the irrational numbers. Let's do irrational number first. Some examples of an irrational number would be like the square root of 7, the square root of 10, the square root of 17, pi, e. There's a number, an exponential number called e. What do all of these numbers have in common? If I were to take a calculator and figure out what the square root of 7 is, or the square root of 10, I would get a horrendous looking decimal. So I'm going to say the definition of an irrational number is now I'm going to pause there for a minute because we need to add to this definition. But if I were to figure out what that decimal is, it's going to be infinitely long, and then something else is going to happen. Quick load this. Let's look at the regular rational numbers. A rational number would be like 7, or 0.75, or 2, or -1, or 3/4, or 0.6 repeating. So an irrational number is a decimal infinitely long that something. Rational numbers, basically the definition of a rational number is that it can be written as a fraction. So if it's possible to write it as a fraction, I'm going to say it's a rational number. Any fraction, any decimal. Now the difference between this 0.6, that bar on top means it goes forever. Well, that means it's also infinitely long, which means what's the difference between this infinitely long number and this infinitely long number? The difference between the two is this is 0.66666. It repeats. 0.22222. It repeats. This one right here, the square root of 10, that infinitely long decimal will never repeat. So if I have a square root that's not a perfect square, then I'm going to call it an irrational number, because another one I could add over here would be the square root of 36. Well, the square root of 36 is 6. So that's the difference between an irrational and a rational. Now, an integer is a more specific version or a more specific set of a rational number. All of my integers are rational, but they contain a different quality than just a rational number. Integers are my positive and negative numbers. So you see how the integer bubble is inside the rational number bubble? That means integers are rational. And then we could look at whole numbers. Whole numbers is a subset of integers. It's a smaller grouping. It's a more specific grouping. Every number that's a whole number is also an integer. So what are the whole numbers? The whole numbers are 0, 1, 2, and so on. So notice how the integers and the whole numbers, they share numbers, right? That's because whole numbers are integers and whole numbers are rational. The whole number bubble is inside the rational bubble. And then we can go one step further. The natural numbers are your very basic numbers. What did you learn when you started to count? When you started to learn about numbers, you counted, right? What did you start with? 1, 2, 3, 4, 5, all the way up to infinity are my natural numbers. It doesn't stop. So it's not like 0 or 1 through 9, it's 1 through forever. So I want to just start and I want to look at some of these examples and I want to determine if it's a rational or it's an irrational And then all of the sets underneath it that each number could belong to. So if I start with part A, I can't just say it's a square root, therefore it has to be irrational. I will say the square root of 81 is 9. Now 9, is it rational or irrational? I'm going to say it's rational. Is it an integer? Yes. Is it a whole number? Yes. Is it a natural? Yes. Now, which one of those categories is the most specific category? Natural. Looking at the next one, 0 divided by a negative 2 is 0. So is that rational or irrational? Is it an integer? Yes. Is it a whole number? Yes. Is it a natural? No, because natural numbers don't include 0. So looking at this, the most specific set is whole number. All right, looking at the next one, 279 divided by 3. That's what I will do first. Is 93, so we're going to simplify that. And if I take the square root of 93, I don't know if you can see that. Then we'll take the square root of, oh, just kidding. We get 9.63, blah, 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 right? This is not a perfect square, therefore it's an irrational number. So remember, part of the instruction was circle the most specific. That one only had one. All right, the square root of 225. Is 225 a perfect square? When I take the square root, I get a 15. So because it's a whole number right here, it goes in evenly. I'm going to say it's rational. It's also an integer. It's also a whole number. It's also a natural number. And the most specific of all of those sets is natural. It's the smallest bubble. Okay. Looking at the next one. I don't even know if you can see that very well. But 176 divided by 64. 2.75. It's a decimal. It doesn't go on forever, so I can say it's rational. But because it's a decimal, it's not an integer. Therefore, rational is the only qualifier here. Now, all of these are real, right? They're all inside of the real box. None of them are imaginary. We're only talking about real numbers. Okay, next one. 68 divided by 40 is 1.7. Again, it's a decimal. Stops in the tenths place, so it's rational. But because it's a decimal, it's not an integer. That's my only set. Looking at this one, we need to simplify that before we can move on. Negative 9 plus 2 is negative 7. Negative 7 is rational. It is an integer. But because it's negative, it's not a whole number, which means integer is the most specific set. And the last one, pi plus 3. Well, pi was in the list of irrational numbers. So I've got an irrational number added with 3 is still irrational. If I'm looking at 6 pi, let's see that. It's still a mother load of ugly, right? Okay, moving on. So let's talk about some of these properties. What happens when we add two rational numbers together? Well, if you ever don't know, just pick two rational numbers and see what happens. So 2 plus 2/3, or 1.75 minus or plus 3.964. Like, these are both just regular rational numbers, right? What happens when we add a rational number to an irrational number? Well, an example of that is right here. It's going to be irrational. What happens when we add two irrational numbers together? Well, if I wanted to do the square root of 3 plus the square root of 2. Both of those are irrational, so the sum will also be irrational. What happens when we multiply two irrational numbers together? So say the square root of 3 times the square root of 2. Well, that's the square root of 6. Well, that's too rational, sorry. Just kidding, back up. What happens when we multiply two rationals? So say 2 times 3/4. Well, 2 times 3/4 is 6/4, which is 1.5, which is rational. What happens when we multiply a rational number with an irrational number? So like rational number 4, irrational square root 7, or 3 times pi, it's still irrational. The last one, though, is a little bit different. What happens when we multiply two irrational numbers together? I kind of gave you that example up here before I scratched it out. So square root 2 times the square root 3. Well, you can multiply those together and get the square root of 6. So an irrational times irrational can be irrational. But is it possible to get it so this right here, when you multiply two numbers together, will be a perfect square? What kind of numbers would have to be out here? Well, let's try like the square root of 7 times the square root of 7. That would be the same thing as saying the square root of 49. Well, this one is a perfect square, which means if I were to simplify that, I would get a 7, right? Which is rational. So come down here, sometimes it's irrational, sometimes it's rational. The when it would be rational is if I had the same thing multiplied by itself. Otherwise, it will always be irrational. Okay, moving on. Hopefully this is helpful if you were absent and needed to view it. I'm sorry that the video wasn't up on Friday. I was having problems with my microphone. I may have to do it like this for a while. Okay, so now we're going to reduce radicals. How do we simplify a radical? Well, this is a radical. Let me point out a few things first. This symbol right here is called the radicand. The number that goes right here is called the index. Now, if there's nothing ever shown right there, the index would be 2. Now, I can take something like the square root of 392 and I can simplify it, because what the square root does is it's taking a number. If it's inside the square root, if it's a perfect square, I can take the square root of it. So looking at 63, what goes into 63? Start with a slightly easier one. 9 times 7, right? And 9 is 3 and 3. Well, 9 right here is a perfect square. It doesn't have to be inside the square root. Because it's a perfect square, I can bring it out. And the square root of 9 is 3. So if I were to list steps on what I would do to simplify a radical, the first step is to make a factor tree. And you need to come down until either you have groups or primes. If you're going to make a mistake, it's because you didn't factor tree it all the way down. So there's a group of 3, and then I have this single 7. I like to circle my groups, underline my 7s. Now notice I didn't circle, well, I didn't circle the 9 really, right? It's because that 9 is the 3 and the 3. I circled the 3's instead. Okay, so step 2, find groups of the same number. We did. Step 3, any groups come out of the radical, any non-groups stay in. So if I were to rewrite this, I've got a group of 3's, it will come out, and then my loner 7 stays in. Now if there's anything on the outside, I can multiply everything on the outside together, and then I could multiply everything on the inside of the radical together as well. Let's try 392. So 392 is 2. If you're ever not sure what goes into it, just start with 2. I know it's even, right? I know it's even, so 2 goes into it. It goes in 196 times. And then 2 times 98. 2 times 49. 7 and 7. So now we circle our groups. I've got a group of 2's right here, a group of 7's right here, a loner 2. Now you don't have to write it this way. I just want to 1 or 2 times to show you what comes out. The 2 comes out, the 7 comes out, and then that loner 2 stays in. What do I do between the 2 and the 7? It tells us right here, multiply everything outside the radical. So my final answer would be 14 square root 2. Okay, moving on. This one, the index is 3, so I'm looking for groups of 3 when I do this one. What goes into 132? Well, it's even again, so I'm going to say 2 times 66, 6 and 11, 2 and 3. Now, this right here means that I need to look for groups of 3. Well, I've got a singles. These are all of my different numbers. I don't have a group of 3, right? Now, if I don't have anything that groups, that means my answer is the problem. This one can't simplify. Now if it was a square root, then those 2's would combine and come out and I would be fine. But because it's a cube root, the index is 3, then I can't. All right, let's look at part D. Part D already has a number on the outside. That's okay. Let's ignore the 2 for now. Look at the 112. 112 is 4 times 28. And 28 is 4 and 7. Now I didn't take those 4's down further because I found groups. I don't have to go all the way down to the primes. If I find groups, I can circle them. 7 is prime, it's a loner. I'm ignoring the x for now. So I already have a 2 on the outside. My 4 comes out. My loner 7 stays in. And the x, if I look at the x, how many are there? Just 1, right? Which means x does not have a group, so x can come out. I mean, strike that, x stays in because it doesn't have a group. So final answer is 8 square root of 7x. Okay, next one. The square root of 225, we did this one on the back page, right? The square root of 225 is 15 times 15, so that's a group. The 6 is already there. The 15 comes out and joins it. Now everything came out, right? When everything comes out, that means the radical goes away. So my final answer is 6 times 15, which is 90. Now variables are tricky because variables change things a little bit. Variables can be positive or negative. Now notice right here, you know, when I take the square root of 63, or if I'm doing this on my calculator, see if I can get rid of the glare. So if I take the square root of 25, oh no, that's not working. It's 5, it's positive, right? If I take the square root of 36, positive, except for I multiply that. If I take the square root of 49, positive. If I take the square root of 100, positive. Maybe, oh, just kidding. Square root of 100 is positive. All of our square roots have to be positive. So variables change things though, because this x right here, or this x right here, could be negative or positive. We don't know. It sometimes is necessary to restrict your answer to only the positive numbers. The function that makes everything positive is the absolute value. The symbol for an absolute value is just that straight up line on both sides. If I put this around here, it means x will always be positive. Now there's kind of a way to remember when you need absolute values, and I'll discuss the rule with you for a minute. Now, but let me point something out really quick. Let's see if I can find a blank sheet of paper. Like we said before, the square root of 25 is positive. The square root of 36 is positive. The square root of 49 is positive. Let's talk about a cube root for a minute. The cube root of 8, well, 8 is 2, 2, and 2. So that's 2, it's positive. Is it possible to do the cube root of -8? Looking up here, is it possible to do the cube or the square root of a -25? No, we can't do that. The reason is 2 numbers have to be exactly the same to multiply to be -25. But 25 is 5 and 5, or yeah, it's not going to work. Because in order to get -25, one would have to be negative, one would have to be positive, and then you don't have a group of 2. They're not identical. But could we get a group of 2 with -8? Well, again, 8 is 2, 2, and 2. That would give us a positive 8. If I change them all to a negative number, do I have a group of 3 that is negative that will get us the -8? Well, a negative times a negative times a negative, there's 3 of them, right? Negative times a negative is a negative. So the answer to this one is -2. What I'm trying to say here is if you have an even index, because the index here is 2, if you have an even index, my answer has to always be positive. If you have an odd index, it could be positive, but it could also be negative. So with the odd index, it doesn't matter if we have a negative or positive solution. Now that's going to be the first qualifier if I need absolute values. There's 2 things you want to check for. The first thing you want to check for is the index even. If it is, keep going, right? Keep checking. So for part F, we're going to have to check to see if it needs absolute values. For part G, we will not because the index is 3. For part H, the index right here is 2. For part I, it's an even index, it's a square root. J, square root, but K, we don't care about absolute values on K because of the 3. All right, the next thing to check for, we're going to discuss in just a minute. Let's hurry and break up this right here, the 128x to the 4th. Here's what we do. Excuse me, 128 is 4 times 32. 32 is 4 times 8. 8 is 4 and 2. Now if we're looking at this, I've got a group of 2's. Let's keep breaking, or a group of 4's, sorry. I was thinking about that too when I said 2. I've got a group of 2's, and then this loner 2. Now what happens to those 4 and that 2? The 4 and the 2 will come out together, and you could write it like this, 4 multiply 2, or you can completely skip that step and just call it an 8. I'm going to leave a space for my variable, but I have this single 2 that will stay in. Now let's look at the variables really quick. Oh, I haven't moved in my classroom for a minute. The lights just went out. Okay, let's look at the variable really quick. I've got 4 x's, right? I'm looking for groups of 2. I have a group of 2 here, a group of 2 here. So all of my x's come out. Going to come out as an x times an x. Now what is x times x? X times x is x squared. So look at that x squared. It's an even index, so I do care about looking for absolute values. And on the x squared, will x squared ever be negative? Anything squared is always going to be positive. So because the x squared is never negative, we do not have to have the absolute values, and this is our final answer. When would this be negative then? It would be negative if the exponent was odd. So going up to our rule, you need absolute values. If the index is even, yes, you're going to keep checking. If the index is even and the exponent outside the radical is odd. I'm going to flip over to your classwork, your homework really quick to give you an example of when this would happen, because, oh no, I have one on my notes. Just kidding, I have one on my notes. That's okay. Let's look at your classwork really quick. Let's look at number 18. 16 is 4 times 4. So I've got a group of 4s. They both come out. B squared is b times b. I have a group of b's. It comes out. Now let's check for absolute values. Is it an even index? Yes, it's a square root. So keep going. When I pull this out, is it an odd exponent? I say yes. Therefore, I need absolute values. That will be my final answer. Okay, let's do it again. We probably won't have time to do all of these examples, but hopefully this will give you a good head start. Let's look at part G. The 72 is 9 times 8. 8 is 2, 2, and 2. I hope that's okay. 9 is 3 and 3. We go until we have either groups or primes. Well, I'm looking for groups of 3 this time. So I've got a group of 3 here, but these don't have a group. The 3s don't. So my group of 2s will come out. My single 3 will stay in. Now x to the 4th. That means there's 4 x's. This group comes out. This loner stays in. It's a cube root. Do we need absolute values? What do you think? I say no, because the index is odd. And at that point, you don't have to keep checking for anything. Let's do 2 more. Let's do part H. Break up the 12. 4 times 3. 4 is 2 and 2. I'm looking for groups of 2 because it's a square root, so that group goes out, that loner stays in. The 2 that's already there stays there. This 2 comes out and joins it. My 3 stays in. Now let's look at the x's. If you want, if it helps you to write them out like this, you can. Circle the x's. A group comes out, a loner stays in. So my answer is 4x square root of 3x. Now, do we need absolute values? First, the index is even, so we might. When I come out like this right here, the exponent is odd, it's a 1. So will we need absolute values? Yes. Okay, one more. Let's try part J. 24 is 4 and 6, 2 and 2, 2 and 3. I know that was fast. The 6 stays out because he's already there. I've got a group of 2s that will join him. We'll deal with our x's in a minute. What stays on the inside? The 2 and the 3. Let's look at the x's now. I've got 4 x's, a group of 2, a group of 2. So it'll be x and x. I've got 2 y's, a group of 2, so y. How do I simplify this then? I've got 6 times 2 is 12, x squared, y, square root 6. Now, do we need absolute values? It's an even index, so I'm saying we might. Now, I have 2 different variables to look at this time. Does the x squared need absolute values? Will x squared ever be negative? Because it will never be negative, we do not need absolute values. But this y right here could be negative. It has an odd power. So I'm going to say yes, we're going to have absolute values on that one. I'm going to give you one more example, but it's not in the notes. Just flip to the back or just watch. You can just watch. Okay, if I were doing the square root, we don't usually put that, of x to the 6th. X to the 6th. Got a group of 2, a group of 2, group of 2. That will come out. You don't have to write this step if you don't want to. A lot of people just kind of aren't used to looking at that and calling it x cubed. All right, doesn't need an absolute value. It's an even index, so it might. Does it have an odd power on the outside? Yes, so I'm going to say yes, it will need absolute values. That would be your answer. Okay, I hope this was helpful. If you have any questions, let me know. The assignment is in your note packet, or in your homework packet, so feel free to finish that up for class next time I see you. And I hope this was helpful. Peace out. Thanks for watching.